everyone. My name is Mahan. I'm a first-year PhD student at the University of Connecticut, and today I'm going to present our joint work with Professor Srini He and Shi Yang, titled as Reinforced Feature Extraction and Multi-Resolution Learning for Driver Mobility Fingerprint Identification. So I would first review our motivations, and then I would define the problem, and then we would go through some of the related works and the existing challenges, and then we would have an overview of our system and summarization of our contributions. And next, I would provide some details about our framework, and then we would have some results and visualization, and finally, we would have a conclusion. So first, I would define unauthorized driver, which is a driver that is not permitted to drive the car for certain reasons. For example, she or he is not included in the insurance policy, or she or he does not own the ride-hailing or sharing driver's account. For example, on Uber, you are not allowed to share your account. And another example is that when you rent a car, other people that are not on the driver's list are not allowed to drive the car. So these are all examples of unauthorized drivers. And why is this important? Because unauthorized drivers may have risky uninsured driving behaviors, and that for the case of ride-hailing services may have some passenger safety issues, or in case of the insurance companies, it would have financial loss for them in case of the accidents. So our goal here is to identify such drivers, which would result in promoting passenger safety regarding ride-hailing and sharing services, or mitigating a potential violation of the policies. For example, insurance companies, by monitoring unauthorized drivers, can further do better insurance rate adjustments. And all of these are done without violating the driver's privacy, like using frequent face recognition checks. So we would first define the problem as driver mobility fingerprint identification that comprises of two tasks. The first one is anomaly detection, where given a trajectory, we have to decide whether it belongs to a specific driver or not. And the other one is driver classification, where we have to specify the exact driver that has generated a given trajectory. So in summary, we have a driver that is producing some trajectories, and we're going to save them on our database and then perform some data analytics on them. And then the results are gonna be fed to our AutoDrive framework for driver classification and anomaly detection. And the results are gonna be given to car insurers and ride-hailing companies, as said before. We divide the related works in two categories. So the first one is driver trajectory data mining, where the related works mostly use autoencoders to extract the features, or use IRL, inverse reinforcement learning, to study the driver's learning process or to predict their working schedules. And the second category is trajectory-based driver identification, where in both driver classification and anomaly detection, the previous works mostly use recurrent neural networks to process single resolution features. Despite previous works, DMF identification is still challenging because in big cities, a lot of drivers may have very similar active regions. And since we are just focusing on GPS trajectories, identifying them may be very challenging. And also, there are some contextual factors like weather conditions and POIs that would affect the driver's behavior indirectly. And these are not considered by the previous works. And finally, one key step in trajectory preprocessing is discretization. And to define the resolution of the discretization, we have to perform extensive parameter tuning, and we may end up losing some information from the trajectory. So this motivated us to use multiple resolutions at the same time, so that we can maintain as much information as we can from the trajectories. So in this figure, we can see the differences of our work with prior work. So we combine the contextual factors with multi-resolution features extracted with spatial-temporal inverse reinforcement learning, and then further process them with multi-resolution and convolutional neural networks. Now we are going to review our framework. The first step is pre-processing, where we remove the noise and perform discretization, and then group them based on time. And the reason behind that is that different drivers may have a very distinct driving patterns in different times of the day. For example, in this figure, at 10 a.m. to 11 a.m. over a month period, these drivers have very different routes taken. So that's going to be helpful for our feature identification. So the next step is feature extraction, where we fit these trajectories into spatial-temporal IRL to extract multi-resolution features, which is then combined with the POIs to create the input mobility fingerprint sensors. So this would be the input to our neural network, multi-resolution trajectory embedding network, MTNet. which is used for driver classification and also used in a Siamese network architecture to perform anomaly detection. We perform spatial and temporal feature extraction with STIRL, and also we process them with multi-resolution neural networks, MTNet, and then we perform extensive data analytics and experimental studies on 2 real-world data sets from Portugal and Italy to confirm the efficiency of our framework. After pre-processing, we perform feature extraction with STIRL. So the input is driver's historical trajectories grouped based on time and a given resolution, and the output would be the rewards and the policy-based maps that represent the driving behavior patterns of the driver and are inversely reconstructed using the STIRL. So here's an example of the extracted features. So the reward and policy are shown on the left side, and the rest are the density of different categories of the POIs on the map. So now to calculate these heat maps on the bottom, which are the actual features, we calculate the intersection of the trajectory and these base maps, and as shown in this figure, to get these heat maps. And this would be the set of features for a single resolution. So we perform this multiple times to get multi-resolution features. We denote our features with F with multiple resolutions, and then you can see the summary of our features in this figure, where HL and WL are the feature resolutions, and the first heat map is the state duration heat map that is created directly from the trajectory and shows the amount of time that the driver has stopped in each part of the trajectory. And the second and the third one are the reward and the policy heat maps created from the features extracted by STIRL, and the rest are created from the density of the different categories of POIs on the map. And we also have a weather feature vector that describes the weather at that specific time and that specific location, like the temperature or whether it's raining or snowing. After feature extraction, we feed them to our multi-resolution trajectory encoding network, MTNet, which comprises of 3 different trajectory encoder networks. So we would have features with different resolutions. Each of them is going to be processed by trajectory encoder network to get the embeddings, and then we also get the embeddings of the weather feature vectors, and then we concatenate them all together and further use them for driver classification and anomaly detection. And each trajectory encoder network is also a multi-resolution CNN network. So each of these trajectory encoder networks process each resolution with 3 subcomponents, each of which are having different complexities regarding their resolution and their filters. So to summarize, for driver classification, we feed the final embedding, the output of the MTNet to softmax function, and for anomaly detection, we feed 2 trajectories and then concatenate the output embeddings and feed them to softmax. So in this case, the 2 trajectories can belong to the same driver in case of a normal case, or 2 different drivers in case of an anomaly. In this table, we show the performance of our driver classification, and we can see that our model outperforms all the baselines. And also we can see that our model, unlike some of the models, achieves good accuracy on both data sets, and considering the fact that we didn't perform any kind of hyperparameter tuning, right, like the resolution to run the model on dataset 1 and dataset 2. So that means that our architecture can be easily transferred to other datasets without much parameter tuning required. And also from this table and the other table, which shows the results of the anomaly detection, that also shows that our model outperforms the baselines. We can understand that CNN-based networks, including ours, perform better than sequential networks like LSTM or stacked RNN. And also, since we label the anomaly class with 1, the high precision of our model indicates that it does not often label a normal case as an anomaly. So this is very important in this problem. So our model with this high precision can be effective in this case. We further visualize some other features learned by STIRL for 2 resolutions given a single time interval. And you can see that each of these resolutions are playing an important role to make the whole input mobility fingerprint sensor more distinct. So these features are calculated for a given time interval and for 2 resolutions. So if you divide a day into, for example, 24 intervals, 1 hour per interval, then we are going to have 24 set of features for each resolution. Now, using the base maps shown in the previous figure, we calculate the trajectory heat maps for some sample trajectories for the same 5 drivers. And you can see that the colors show the learned features for each driver in different parts of the map. And even if 2 trajectories belonging to 2 different drivers are happening at the same location with the same shape, the model is still going to distinguish them because the features learned for each driver at different parts of the map is distinct. And that shows that our model is working. In this work, we just focused on GPS trajectories, but our framework is general enough to be integrated with other sources of data, like the ones from smartphones or wearable devices or CAN bus. And then we can also consider the possibility of more fine-grained anomaly detection like DOI in our future works. So in conclusion, we designed a feature extraction method that extracts driver mobility fingerprints using inverse reinforcement learning with multiple resolutions, and then we further process them with multi-resolution neural network, and we perform experiments on 2 real-world data sets to show the efficiency of our RM-derived framework. This would be the end of our presentation. Thank you for your attention, and you can visit our lab's website if you're interested in our future works, and I would be happy to answer any of your questions.